All right, I think we left off. Oh, it was the stability part, I think, that we were talking about. So let me see if I can expound on that. Right. So we were talking about the alkene stability and the substitution, like how substituted the alkene is. And so when we think about we're talking about percent S character. Right, so it's the SP3 is 25% S, SP2 is 33% S, and then SP 50% S. We talked about that in a previous session, right? So when you have those for alkene like this, right? Those carbons here, they're sp2 hybridized, right? And because of that, a couple of things happen. One is that this bond length is going to shorten. And the reason the bond length shortens is because those two carbons are, because of their increased electronegativity, right? The bond length shortens because those two atoms are more electronegative. So each one of them is pulling on the electrons of the other, right? So that bond length kind of gets more compressed. The other thing about those two carbons is that because they're sp2 hybridized and they're more electronegative than an sp3 carbon, right? You can stabilize them by adding in electron-rich groups, like adding a methyl group, a carbon-carbon single bond, right? Those bonds get polarized, micro dipoles, not really super overly polarized, but they'll have like a little bit of a dipole where this carbon becomes partially negative and this one becomes partially positive, right? And this is strictly because that carbon is sp2 hybridized. So because it's sp2, it's more electronegative. And we know when we think about the definition of electronegativity, what comes to mind when you think about the definition of electronegativity? What do you think?
Able to hold electrons closely.
Yeah, or more desirous of electrons, right? The more electronegative an atom is, the more it loves electrons. And so when you put an electron-rich group on that electronegative atom, then it's going to cause like an inductive effect. So all of those carbon-carbon bonds being electron-rich, they're going to be polarized towards the sp2 carbon. So the more you put around it, the more stable it is, right? Because it's like you're feeding a hungry atom, hungry for electrons. So that's why up here when we talked about the stability of an alkene, we talked about the substituted alkene being the least stable, and then the tetra substituted alkene, which is on the end, being the most stable because it had the most groups around those two hungry carbons that are hungry for electrons, right? And so that's why the more substituted alkene is more stable because of that. Those sp2 carbons, when you attach some electron-rich group, and in this case, you're attaching a carbon-carbon single bond, right? Those carbon-carbon single bonds are going to get polarized towards that sp2 carbon. And the more of them you put on there, the more stable that carbon becomes.
Okay, that makes sense. But would you be able to do it for any other hybridization group? I know it's probably not likely for the sp3. But...
Well, with sp, I mean, you can think about it like a sp hybridized, because really sp3 is going to be like carbon in its natural electronegativity state, right? But sp, because of the hybrid and how the electrons are getting closer and closer to the nucleus, and the atomic radius is going down a little bit. With that, that's when you start seeing the electronegativity increase, right? And then sp, with that, those electrons being even closer to the nucleus, that's you see again the increase in electronegativity. So with that, you can think about the same thing, right? If you have an sp hybridized carbon, like you have something like this versus this, right? You can think about the carbon-carbon sigma bond again. This is sp, so it's going to be more electronegative. This bond between those two carbons in the triple bond is a little bit shorter and a little bit more compressed. So the adding in an electron-rich carbon-carbon single bond is going to have the same effect, right? It's going to have a little bit of a polarization or a little induction towards the carbon that's sp hybridized. But with sp3, you don't really see that because the electronegativity is not, it's not so much increased for sp3 carbon. But you start seeing it increase as you go from sp3 to sp2 to sp, if that makes sense.
Yes, it does. So it's more likely to happen for sp than sp3.
Yes.
Okay.
All right. So there's one other thing I wanted to talk about with, so we talked about Zets rule. We talked about what's major, what's minor. Let's recap that. So for this alkyl halide, when we did the E2 elimination, the tri-substituted alkene was the major product. And then the di-substituted alkene up top, you can see the double bond highlighted in blue. And then the carbon that's highlighted in pink on the left and on the right, those are, that's two carbons, so it's a di-substituted alkene, right? And then you look at the one on the bottom that's tri-substituted, you see three carbons highlighted around the double bond, right? So this is, according to Zaitsev's rule, this is what we call a major product. And then this, what we would call the minor product. All right, so we talked about the fact that the E2 is concerted, and what the rate law will be is just like SN2, it's bimolecular, so it's going to have a two-term rate law. So let me show you a couple of other things relative to the E2, and I'm gonna put the page here. Date on that too. Right, so there are two other ideas that we want to talk about here. And one of them is what the transition state looks like, since we talked about the transition state for all the other two mechanisms. And what's happening in the transition state again? Anybody?
Isn't he's giving the electrons?
Yeah, so in the transition state, there are bonds being made and there are bonds being broken, right? So it's the highest energy point on the energy diagram, and it's where your bonds are being made, and well, they're being made and broken on the way to the transition state. But that's where your bonds are um, effectively being your star materials are effectively being converted into your products. And depending on whether it's exothermic or endothermic, that's going to determine whether or not that transition state looks like the star materials or the products. Remember the Hammond postulate. It says that whichever species the transition state is closer to an energy, then that's what it's going to resemble. So if it's an exothermic reaction, it's going to resemble the starting materials, and if it's endothermic, it'll resemble the products. All right. So let's look at what the transition state would look like for the E2. And with this, I'm going to talk about one other thing that's important. So this will be my leaving group. This is my alpha hydrogen. Different pen. Right, and then let me move this down. Right, so my base is going to come in. I'll just keep using OH. And it's going to donate a pair of electrons here to do proton transfer. So that's a partially formed bond, right? The CH bond is going to get broken. So that's partially broken. Uh-oh. Right? I'm also forming a pi bond. So I'm going to put a partially formed pi bond here. And then I'm also breaking the CBr bond. So this is forming. This is breaking. That's forming. And then this is breaking. Right? That's what the transition state it looks like for E2 elimination. Also, with one other feature of the E2 that's important is here. Right? So the bromine and the hydrogen that are here, they have to be on opposite sides of one another. So the alpha hydrogen that's here, let me write that in. Right, the alpha hydrogen, it has to be on the opposite side of where bromine is. So we call that anti periplanar. So I'm going to show you another way to look at this, another way to depict it through what we call a Newman projection. Right. So if you take a carbon bond, right? Normally when we think about this, right, it just looks like that. We just write those hydrogens out, and we don't really consider the angle the bond angle. But you could also think about this if I look at it kind of from the side. So here's a carbon, and here's a carbon. This is what we call a sawhorse conformation. So this is H, 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 and H, H, and H, right? So when you think about the Newman projection, the Newman projection is basically you take these two carbons right here, change the color there, this carbon and this carbon, and you're going to look down the carbon-carbon bond. So the Newman projection actually would look like this. So we're going to make that, I'm going to change the color on one of those. So we're going to make that purple carbon the front carbon. So on a Newman projection, it looks like this. So this is the back carbon that we had as it was teal. Right? And then that front carbon is right here. Right? So it's like we're looking down the bond, so straight down the bond, so that we see one of those front, we see that purple carbon right in front of our face. All right. And so when we put the hydrogens on, we can put them on like this. And then on the back carbon, I'm going to put them like this because this is the most stable Newman projection. And you can do this for any two carbons in a chain, right? This is what we call the staggered conformation. Right? So if it's staggered, all of your hydrogens are 60 degrees apart. Right? We call that gap between those hydrogens, that's 60 degrees. We call it a dihedral angle. Right? That dihedral angle is 60 degrees between all of your carbons. All of your hydrogens. Right? So the back carbon is the teal turquoise color carbon, and the front carbon is the purple color. All right. And it's like we're looking down that bond. Right. So when you think about the Newman projection, these two groups right here, let me show you that. Come on, I need you, battery. Don't do that. This hydrogen and this hydrogen, you see how they are apart from one another? Like the distance between those two hydrogens is at 180 degrees. So we say that those hydrogens are in the anti position. So right, let me change this. Those two hydrogens right there, we say that they're anti to one another. So 180 degrees between them. All right. So when we say that the leaving group and the alpha hydrogen have to be anti-periplanar, that means that they have to be on opposite sides of the same plane, or they have to be 180 degrees from one another. So if we looked at that particular alkyl halide, we could draw the Newman projection like this. This will be my back carbon, and then this is my front carbon. I just designated with a dot. All right, so I'm going to put my bromine here. Then I'll put the other two hydrogens here. And then one of my alpha hydrogen that I want to remove, I'm just going to put it right here. So this is This is my alpha hydrogen. This is my leaving group. And you can see that they are 180 degrees from one another. So they're anti, right? So in order for the E2 elimination to happen, your leaving group and your alpha hydrogen, they have to be anti-periplanar. They have to be 180 degrees from one another. So for E2, the leaving group and the alpha hydrogen must be anti-periplanar. There are some instances where an anti-geometry is impossible to adopt. So if that's the case, then, and I'm not going to get into that here because I don't want to get too deep in the weeds with these conformations because we're going to do a whole section on that. But I want to introduce it because that's the way to think about these E2 elements. It's a good way to visualize like the conformation that's necessary for the elimination to happen. So for this to happen, you have to have your alpha hydrogen and your bromine or your leaving group. They have to be anti-periplanar to one another. All right, any questions about that? Now the Newman projection is, it has some what we call mobility. So there are other conformations that are possible, but for now, we're just gonna talk about the stagger, right? That's the lowest energy conformation for a given Newman projection, unless it's a highly substituted compound. But for now, we're gonna just leave it, park it right there. Any questions about the transition state? Any questions about the, I forgot to put this in here. So this is partially negative and this is partially negative. So the overall charge on the transition state is negative. All right. Any questions about anything, whether it's the Newman projection or anything else concerning E2?
How do you know how to, I guess, necessarily draw it, like the Newman projection like that?
For just for the alcohol halide that we have right here.
Yes.
Yeah, so there's a, let me I'm trying to do that. So that alkyl halide, it was just 2 carbons, right? And then right, so for that, you can draw multiple Newman projections, right? Let me show you. Let me just go through 1 or 2. I'll go through 2 of them. So one of them, let's say the back carbon, we're going to leave because when you're doing Newman projections and you are no, not that. Put the BR over here. Right, this is a possible Newman projection also, right? But if I'm trying to line the bromine up with this hydrogen, even though the other alpha here now is lined up with that one, but that's not what I want to do. I want to show it to where they're to make it more visual and show the alpha hydrogen that's highlighted being anti with the bromine. So we're not going to use this one, right? But there's mobility around that carbon-carbon single bond, right? So this is one conformation. And then if I rotate 60 degrees, right, this is staggered. I'm going to end up at another conformation, which is not as stable, which we call the eclipse conformation. So the back carbon is going to stay the same. And then the front carbon, the hydrogen here is going to come around. So this one is going to swing around to here. This is going to swing around. And then this hydrogen is also going to swing around. And then they're going to be overlapping. So that's that. And then bromine is now here, right? This is an unstable, this is what you call eclipsed, right? What that means is that all of your atoms are overlapping with one another, right? And the angle goes from 60 to 0. One second. All right. So the angle goes to 0, the energy goes up. And so then you can actually rotate around that bond again, another 60. And that's going to get you to, oh, hold up, I need to add another page. All right. So if I rotate again, and I'm gonna move all this before I post it, right? Around. So I'll take each one of these. I'll take this carbon, I rotate it this way again by 60 degrees, right? I'm going to get to another staggered conformation, but bromine is going to be in this position right here. So that's how I was able to draw that, because I know that the dihedral angle is 60, and I can rotate multiple times around that carbon-carbon bond. And it just moves between those different conformations, and they all have different energies and things like that. So that's how I knew to draw that way, right? Anytime you have a Newman projection, it's mobile, like there's conformational mobility. So you can move the front carbon, you can rotate it, and that carbon-carbon bond gives you some free rotation. And you just oscillate between staggered and eclipsed conformations.
So the first one is I guess, more ideal.
Say that one more time.
The first one is the more ideal.
Yes.
Solution.
Yeah, staggered is always less energy than eclipsed. All right, great question. All right, let's talk. We talked about the E2 already. I want you to do this one on your own. If you have a problem with it, then just reach out, but I want you to at least attempt it. Let's go to the E1, which I didn't cut, I don't think. The E1 is Penn Russell. I'll put a new page in. So the E1 is different from the E2, right? Much different. It really follows the same pathway as the SN1 reaction, right? So tertiary, secondary carbons work. You want a protic solvent. Tertiary is favored because of the stability, carbocation stability, and it follows, just like E2 elimination, it follows Zaitsev rule. So for E1, there's no base necessary, even though it's an elimination. Right, no base. Right. Also with the E1, your substrate, it can be tertiary or secondary, right? You don't want to use a primary substrate because this follows almost the exact same path as a SN1, in that you lose your leaving group first, and then you form a carbocation intermediate. So you can see right here, this is done in sulfuric acid, right? So that's protic. We know that's protic. So we know it's not going to be an E2. If you try to do a E2 elimination in a protic solvent, the only thing that's going to happen is the base that you're using is just going to do proton transfer with the solvent, right? So the solvent is going to be competing with the substrate to donate a proton, right? And if the solvent is really acidic, then no elimination is going to happen. But that's not a problem here because there's no base, right? So this is going to react first with sulfuric acid. And I know I said that we said that the first step is loss of leaving group, but in this case, OH is a bad leaving group, right? It's a terrible leaving group. So you have to make it better. The way you make it better, one of the ways anyway, is to convert it into water, right? So if this is here, this is going to do proton transfer with the acid. And so you end up with hydronium ion, right? Anytime you have a water attached like this, it's called a hydronium. When you see that suffix IUM, that's normally indicative of a cation, something with a positive charge. If you see the suffix IDE, that's normally indicative of something that has a negative charge. All right, so this is a hydronium ion. And that is going to lose water, right? And give me a carbocation intermediate. Up to this point, this is all identical to SN1, right? So this is the rate determining step though, right? Just like SN1. Loss of my leaving group is the rate determining step. So just like SN1, this is going to be a unimolecular reaction. With an identical rate law. K times the substrate. All right. And then now this is my intermediate that's going to get deprotonated. Where proton transfer is going to happen. So this is alpha. This is also alpha. And then now the question is, how does it get deprotonated? Because you lost water. But you also have the conjugate base of sulfuric acid. Right? So you got the conjugate base of sulfuric acid plus water. Both of those can act as a base. Right? So there's no external base necessary, but in order to do proton transfer, something has to act like a base. So it can be either one of those, right? The simplified version is just to use the conjugate base of sulfuric acid, right? So let that do your proton transfer in the second step. So to eliminate, so we'll just take that proton and we'll take those electrons and put them there, right? And so from that, we're going to get this product, where there's an alkene here, plus water, plus sulfuric acid, regenerated, right? So again, with this particular example, you protonate the hydroxyl group, lose it as water, which is still a rate determining step. And then you eliminate either using conjugate base or water, which left as a leaving group. Both of those can act as a base in this case. But that's the gist of the E1. It follows the same pathway as SN1. And in this particular case, the energy diagram is going to look something like this, where you have a really fast first step, followed by a slow step, followed by another fast step, right? So this is your hydronium. Right? This is your carbocation. And then this is your product. These are your start materials, right? So if this is an approximation. Now, I'm not sure what the actual activation energy is for each step, but the slow step has to have a higher activation energy than the other two steps. Otherwise, it wouldn't be rate determinant. So that's what the energy diagram would look like. Is this stepwise or?
Stepwise.
Yeah, it's stepwise. Right? Because the rate determinant step happens and it's not concerted with the elimination, like the loss of leaving group happens first and then the elimination happens. That's why we consider it stepwise. All right, questions about the E1?
Can you repeat what you just said about the stepwise? Why it's stepwise?
Yeah, so the rate determinant step, you see how the leaving group leaves first, followed by the elimination.
Okay.
Yeah, so that's why we consider it a stepwise mechanism. Even though you have a step here where you do proton transfer, we can't forget about that. But this is not the rate determinant step. It's the loss of leaving group that's rate determinant, and it happens. So you get a carbocation followed by elimination, as opposed to it all happening at once like the E2. So we consider this a stepwise mechanism.
Can you explain where the leaving group leaves? I'm not seeing that.
You mean like, so right here?
Oh, it turns into water. Okay, I got it.
Yeah. So you convert that into water by doing proton transfer with the acid, with the solvent right here. And then when you do that, you turn that OH into a hydronium ion, which is a much better leaving group. If we look at the chart for leaving groups, let me zoom out and find chart. Right, you can see right here, OH, where is it? When you compare OH to water itself, big difference. You see that? Huge difference. It's really about 16 times. Water is literally the conjugate acid of water is 16 times more acidic than the conjugate acid of the hydroxyl group. So that's why it's such a much better leaving group. And 15.7 is not horrible as a pKa for the conjugate acid of hydroxyl, which is water itself. But the hydronium ion is just a much better leaving group. All right, any other questions about that? I think we're at a point now where we can go and start working through some of the examples. This page right here is just kind of a summary of the concerted versus stepwise mechanisms for substitution. So you can look over that. It just has like everything summarized. But let's look at some examples and see if we can apply this, right? Let's go here first. It says for each pair of the following compounds, identify which compound will react more rapidly. So that's your question right there. what's going to be faster in an SN1 reaction. So it's telling you the mechanism, right? It's SN1. What do we know about the SN1 mechanism? We know that it's favored in protic solvents. We know that tertiary, secondary, and allylic substrates are faster. And we know that it's also favored with good leaving groups. All right. So if we go right here and compare these two, this is my leaving group in both cases. In one example, that leaving group is on a primary carbon, and here is on a tertiary carbon. Which one do you think is going to be faster?
Would it be the primary one?
Okay, let's think about that. Think about what happens in an SN1 reaction. What's the first thing that happens? For SN1, remember, I'm gonna do a generic
The leaving group leaves.
yeah, the leaving group leaves. That's your rate determining step. So then if we expound on that, loss of leaving group is going to create a carbocation. Right, you get a carbocation. Would you rather have a primary carbocation or a tertiary carbocation? That's the question for this example. Which one is going to be more stable?
Tertiary?
Tertiary. So which one do you think is going to leave faster?
The tertiary?
The tertiary, right? This is a faster reaction because the intermediate that you make is more stable, right? If you make a primary carbocation, remember this, the trend, tertiary is better than secondary, is better than primary, which is better than methyl. So a primary carbocation is one of your least stable carbocations. So if you're trying to, not that an SN1 is going to happen on a primary, but it's just for the sake of the question. If you're trying to do an SN1 on a primary, it's not going to happen, right? Because making that primary carbocation is going to be, for lack of a better expression, is cost prohibitive, right? It costs too much energy to make that cation. But the tertiary is going to happen spontaneously because that cation is going to be much more stable. All right, let me write that in here somewhere. All right, so the one that's circled is faster. Let's look at the next example, B. This is my carbon that we're comparing, right? Because the leaving group is attached to. That's what a leaving group is. So this is, here's my bromine leaving group on each one. What do you think?
The second one?
Mm-hmm. This one, right? And the rationale is the same, right? It's a tertiary substrate. SN1, the SN1 reaction, the mechanism favors a tertiary substrate because of the carbocation formation. All right, so if it's SN1, tertiary, a tertiary substrate is going to be faster. All right, what about C? What do you think? Same leaving group. What's different about those two?
There's an alkene one.
Right here, right? What does that mean for this carbon? What do we call that if it's adjacent to an alkene? What's the term? It's allylic, isn't it? I know y'all been like, dang, we've been everything is allylic, but it's not. We talked about this term before. When you compare those two, right? This is and then both carbons are secondary. But the fact that this is allylic, when I make the cation, well, I'm putting the cation here versus here. What can this allylic cation do that the other one can't? It's quiet like church during prayer time.
Can it like transfer something?
Can they do resonance?
Yeah, like move an electron or something over.
Yeah, it can do resonance with that pi bond, right? And stabilize that positive charge. So now this goes to here. Right, so this cation is stabilized by resonance. Right, the other one isn't. So this is going to be faster. Right, remember, the SN1 is going to be faster if that carbocation is somehow stabilized by something, by resonance, whether it be by hyperconjugation or additional substituents on it, whatever. If you're making a stabilized carbocation, then that reaction is going to speed up. If that carbocation is not stabilized, then it's not going to increase the rate of the reaction. All right, we got to stop right here. I got a bunch of stuff to upload for y'all too, because I didn't put the Wednesday stuff on YouTube yet, didn't put the notes up, anything. But I'll put, since the notes from Wednesday and today are combined, I'm just gonna upload that once. But the videos I'll upload shortly. All right, any questions about anything